Alright, today we're going to be looking at doing some integration, some calculus actually. We're going to be looking at polynomial integration, and we're going to be exploring antiderivatives. So there are multiple types of integration. There's some pretty high-level stuff that you'll see in physics, but for now we're just going to be looking at, again, polynomial integration, and we're going to be doing the two fundamental types. The first type is definite integration. Definite integration is the type that explores the use of antiderivatives to find the area under a curve that is or is not linear. And on the topic of antiderivatives, the rule is if we want to integrate something, find the antiderivative of x to the n, it's going to be x to the n plus 1 all over n plus 1. And then, since we're still in definite integration, the rule, if we want to integrate something from lower limit a to upper limit b, we want to integrate any function, we'll call this a function of x, f of x. This is going to be the same thing as the antiderivative of b minus the antiderivative of a, the difference between these two. And these are just, this is almost like slang, because f is a function of x, we say that the capital F is their antiderivatives. And so again, definite integration deals with integrals that have an upper limit b and a lower limit a to find the area under the curve between those two x values. And he does that by using antiderivatives up here. Now the other type is indefinite integration. Indefinite integration is going to integrate functions that you give it using antiderivatives, but it's not to find the area under the curve. Essentially what you're doing with indefinite integration is you are taking the order of the polynomial, in this case, of whatever function it is, and moving it up by 1. And you are adding a plus c constant at the end, the family of curves there at the end that you have to add to make things work. We'll get to that in a bit, but both of these do use antiderivatives. But definite integration, of course, only applies to definite integration here. Okay, now that we've gotten to understand the basic idea of what we're looking at with integrals, we're going to do an example with definite integration. And I'm going to do two examples like this to try and show you why this is necessary. Why it's necessary to do a calculus, that is. So we're given a function y equals x, f of x equals x, same thing. And we are to find the area under the line from x equals 0 to x equals 3. So if I graph this, 1, 2, 3, just have a slope of 1. If I graph this, we use the handy dandy line tool over here. My job is to find this area, 1, 2, 3. This is a figure, the area, the shaded area is what I'm being asked to find. So of course we have a 3 by 3, not truly a 3 by 3 area, but half of one. And what is this? What can we use this? What is this? Well, this is a triangle, right? We don't have to use calculus in an instance like this because we have a linear thing. And what's the area of a triangle? Area of a triangle is just, of course, 1/2 base height. So in this instance, we can apply that here. We just say area equals 1/2. The base is 3 here. The height is 3. 3 times 3 is 9, times 1/2 is 4.5 units of whatever we want to measure that in. So this is an example where we have a linear equation and we want to find the area under that curve, where we don't necessarily have to use an integral or any calculus at all to find this, because we can treat it as just a geometric figure that we know how to take the area of. If we wanted to do this calculus way, we could say the integral from 0 to 3 of x dx. That's how we would write this up here, and then we would just solve antiderivatives that way. And so this is an example. It's a good way where sometimes you'll be given a graph like this, like, oh, this is easy, that's great. Other times we're going to be given an equation like this, where when we graph it, we're going to see that it's not necessarily linear. It's not linear, in fact. It's going to be a cubic function. And so if I try and draw the line here, try and connect the dots best I can. Didn't do too great of a job there, but you get the idea. This is not a straight line, so what are we going to do? What are we being asked to do here? Let's get a feel for the question. Find the area under the curve, so it's not just a line anymore, now it's a curve. from x equals 0 to x equals 4. So I'm being asked to find 1, 2, 3, 4, 4, all of this area, and then up to wherever it would meet this graph, because it would eventually meet it going up infinitely. But how do we solve this? Even if we could see where these two met, how would we solve this? This isn't something like a triangle where the area is 1/2 base height. Like, that doesn't work. It's not a trapezoid or anything. It's not a rectangle. It's not a cube. So how do we do this? This is why calculus is necessary, because there's no area formula that we can use or derive ever to find an accurate representation of this. We can do something maybe like a Riemann sum to maybe get close, but in reality, we're still not going to be getting a truly accurate answer. So this is where Isaac Newton and his calculus comes in. So if we want to write this question, why don't we draw a little arrow down here? We are being asked to find the area under the curve from 0 to 4. Actually, let's make this a little bit smaller. Area under the curve from 0 to 4 of x cubed. Again, we omit the y equals here because it's implied that it's there. Dx. This is the same question here. The lower limit's here, upper limit here, and we see that upper limit is up here, lower limit is down there. So remember our antiderivative rule. The antiderivative rule is going to be x to the n. Dx is just going to equal x to the n plus 1 all over n plus 1. Let's not forget this. So if we apply this over here, well, we turn this into some numbers we can use. So we can see that if we go n plus 1 is 4 here, right? We keep x the same. X, 3 plus 1 is 4. And the exponent up here is the denominator down here. X plus 4 over 4. And then to put this in proper notation, we would just do from 0 to 4. And this is the same thing as this. These are interchangeable here. But in order to get an answer, we need to be able to put into our calculator, right? Let's expand this. It's going to be, let's draw a different bracket here. It's going to be 4, because the upper limit is b, and remember our rule was the difference between antiderivatives between b and a. 4 to the 4th over 4 minus 0 to the 4th over 4. And of course, putting the 0 there is a little bit redundant, but we have to get in the habit because this will not always be 0. So let's just get in the habit of doing that. So if we put this in our calculator, x cubed, we're going to get exactly 64 units, or whatever we want to measure that in. So this is going to equal this. This is also going to equal this. This is also going to equal this. These are all a form of the same thing, but this is the number. This is the version we can compute with raw numbers we just put into our calculator. You don't have to draw the bracket hierarchy here like I did. I do that for organizational purposes. And yeah, we get exactly 64. So as it turns out, if we were to count up all of the infinitesimally small spaces underneath this curve, from 0 to 4 on the x-axis, we would get 64 exactly. Calculus is wild like that. We'll do some more examples next. Alright, so for our first practice problem, to make sure we understand definite integration, we have this right here, this little behemoth, this mini beast. Don't let it scare you at first. It's really simple. We're going to go term by term. Before we do anything else, let's make sure we remember our antiderivative rule. The antiderivative of x to the n is going to be x to the n plus 1 over n plus 1. And then if we want to integrate f of x from a to b, our difference is going to be antiderivative of b minus the antiderivative of a. Let's not forget these. I might have to erase these if I run out of space, but let's just keep these in mind as we do this problem. Okay, so we're going to go, like I said, term by term. So we have 1, 2, 3, 4 terms to deal with here. And as a unique, property of integrals, we can do term by term and add them at the end. So that's what we're going to do. That's the easiest way. Let's start off with the antiderivative of 5x to the third. Using our rules here, this top one, the antiderivative of 5x cubed is going to be 5x to the 4th over 4 from 0 to 3. We can do the same process for 2x squared. It's going to be 2x cubed over 3, of course from 0 to 3, plus 3x squared over 2, 0 to 3. And anytime we have a constant, you can do the process. It would just be 4x to the first over 1. But that's a little bit redundant. We just do 4x from 0 to 3. Now, remember when I talked about raising the order of the polynomial by 1? For indefinite integration, that's true. For antiderivatives in general, that's also going to be true. Notice this goes from a 3 to a 4. This goes from a 2 to a 3. It goes from a 1 that's there to a 2. This goes from a 0, there's no x, it would be x to the 0, to x to the first. So that's just a neat product, a neat property of antiderivatives. So if we expand this, I'm not going to do all of them because we understand the expansion process, I'm sure. If we expand this, it's going to be 5 times 3 to the fourth over 4 minus 5 times 0 to the fourth over 4 plus 2 times 3 cubed over 3 minus 2 times 0 cubed over 3 dot dot dot. That just means for the rest of the terms here. And if we were to do this for all the other terms, put this in our calculator. We can use calculators here to make it really easy. 5x cubed plus 2x squared plus 3x plus 4 dx. We're going to get exactly 144 3/4 units, whatever we want to measure that in. That is the answer to this problem. 144.75, 144.75. So notice all we did is find antiderivatives for each term on a term-by-term basis, and then added them all up. We added up whatever the antiderivatives would equal. I didn't expand all of them here because it's the same process, but the dot 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 again implies that we did do that for all of them. And it's a really simple process once you get the hang of it, and we'll do one more problem like this before we move on to indefinite integration. Okay, now we're on to this problem here, this little behemoth again. It maybe looks a little bit scary, and that's okay. We have a radical here, we don't have a 0 here, we have a 7th power all the way up here. So it's got some different things from the last one. And this is one where we have to include all of it when we do calculations because the lower limit is not 0. And the first thing, because there's a radical here, the first thing that I can't recommend enough doing, it's probably the best thing you could do here, write out your integral again, but turn this radical into a fractional exponent. So 3x plus 7 minus 13x cubed plus 4x squared minus x to the 1/3 power plus 1 dx. I'm not going to write our rules here because we might run out of space and I might need that, but all we did between these two steps is we turned cube root of x. We turned the cube root of x into x to the 1/3 power, which is the same thing. If you were to plug x, any number for x in here, solve that same number here, you get the same answer. This is the same thing. And we just do this to turn everything to an exponent to make it a little bit easier to visualize. Of course, this is an optional step. I always do it. It makes it easier. It's really something I recommend doing. Okay. So let's get started with finding antiderivatives. So we're going to do the same process. Remember antiderivative rule, same as ever. X to the n dx. That's not very good. X to the n dx equals x to the n plus 1 all over n plus 1. Hopefully you can see that. Same rule we've been using the entire time with these sort of problems. So let's find the antiderivative of every term. 1, 2, 3, 4, 5 terms this time. Nothing special, nothing different. We're just going to go about it the same process. So the antiderivative of 3x to the 7th is 3x to the 8th over 8 from, of course, negative 2 to 3 minus, and we're going to keep these same signs. They're going to be equal to each other because I like to just add everything up as it is. So minus 13x to the 4th over 4, of course from negative 2 to 3, plus, signs are the same, so plus 4x cubed over 3, minus, this is where it maybe gets a little bit tricky, but it's nothing we can't handle. So we have x, and then we have to add 1 here, because remember it's n plus 1. What's 1/3 plus 1? It's going to be 4/3. So 4/3 divided by 4/3 from negative 2 to 3, negative 2 to 3, and then remember with any constant, we just have that as 1x, or just x, either way, to negative 2 to 3. So once we expand all of these, I'll start the first half over here, the first part of it. It's going to be 3 times 3 to the 8th over 8, or brackets in here, minus 3 times negative 2 to the 8th over 8. And this is why, remember, we have to keep in the habit of doing both antiderivatives, because this is not always 0. Here's a case in point example of that. We're going to do the minus here. Minus 13 times 3 to the 4th over 4 minus 13 times negative 2 to the 4th over 4 dot 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 for all the rest of the terms, meaning we did that for all of them. And we put this into our calculator, because this is going to be one, especially with the 4/3 here, we have to understand. We put this into our calculator. It's going to be negative 2 to 3, 3x to the 7th minus 13x cubed plus 4x squared minus the cube root of x for x to the 1/3 power plus 1 dx. Let it think for a second, get all that special math magic done, and when we calculate everything, compute everything, it's not going to be a nice even whole number or even a nice even decimal. It's going to be, I'm going to make this approximately equal to 2,203.44 units, and that is our answer. So if we were to graph this function, we'll call this f of x equals this entire function here. If we were to graph that and then find the area under the curve from negative 2 to 3 on the x-axis, this would be the area under that curve. And that's exactly what we did here. Alright, so we finished the little section on definite integration, so now we're going to move on to indefinite integration. So I've got some bullet points lined out for us here, kind of going over what we discussed at the very beginning. So indefinite integration increases the order of the integrated polynomial function by 1, and that's once per integration. So if you have multiple integrals, it's going to increase by however many integrals there are. The order of that polynomial function is. It is not going to have upper or lower limits, and so what that's going to mean is that no longer are we going to see integrals that have anything from like 0 to 3 or negative 2 to 3. That's not going to be happening anymore. Instead, we're going to be seeing just an integral with a function here, and then da 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 da, whatever else after. We're not going to be seeing upper and lower limits, because in reality it's just going to be infinity to negative infinity, and that's why the order increases by 1. And of course it does use antiderivatives. That's how integrals work, or using antiderivatives here to help us out. But again, it doesn't increase or doesn't compute the area under the function's curve. So f of x, even if it's, maybe the graph looks something like this, whoa, and it goes down, something like that, it's not going to find any of this area. Instead, it's going to increase the order by 1. And as it does that, it's going to add a c constant, the integration constant, to whatever it integrates, whatever function integrates, and that's to increase, or not to increase, that's to go along with this in correspondence with that. That's just a little rundown on what we're going to see. Remember our integration rules for an antiderivative. We'll make sure to do this. Antiderivative of x to the n dx is going to be x to the n plus 1 over n plus 1. And this is going to be really important going forward. Okay, so we're on to our first practice problem here, doing our first part of indefinite integration. So right here we see everything is just four terms we have right here. Everything is already an exponent. No need to rewrite anything, so we can just go ahead and get right to finding our antiderivatives. Remember, I know we've gone over this a bunch. X to the n, the antiderivative, is always going to be x to the n plus 1 over n plus 1. If you do not have this memorized, memorize this formula. Very, very important in calculus and in general, in math, beyond calculus, physics, whatever. So we're just going to go ahead and find our antiderivatives. Antiderivative of the first term is x to the fifth over 5. Second term is minus 5x to the fourth over 4 plus 7x cubed over 3 minus 1x, but that's a little bit redundant. We just put x. And remember, whenever we do indefinite integration, we must add that plus c. Always, always, always. So we have our plus c there. And we don't have anything else we need to simplify, but we'll write it just to make it a little bit nicer. And it's just going to be 1/5, just so we have fraction coefficients in front of everything. 1/5 x to the fifth minus 5 over 4 x to the fourth plus 7 over 3 x to the thirds minus x plus our integration constant. And this is our final answer for this question. Really easy, really simple. Just make sure we don't forget our c constant at the end. Okay, so we're back doing a second indefinite integration practice problem, and wow, look at this thing. It's crazy. First thing that catches my eye here is we have the 19th root of x to the 23rd. Now remember, this looks a little bit scary. It's long. It's got 1, 2, 3, 4, 5 terms here. Looks a little bit scary at first, but that's okay. Remember, write things out, follow the order, find the antiderivatives, and it will be okay. So what do I recommend doing whenever we have a radical like this? We write it out again. So I'm going to go ahead and write my integral again here. 5x to the 8th minus 12x to the 6th plus 7x to the 5th minus x to the 23rd over 19 power plus 3, and then of course dx at the end. Now again, this step completely optional. I always recommend doing it because all we do is turn the 19th root of x to the 23rd into x to the 23rd over 19th power. This is the same thing. Again, if you were to plug in any number of x here for this one, you get the same thing in your calculator. So same. So we'll just keep that there. It's a nice step I always make sure to do. And so from here, we can just find our antiderivatives. I'm not going to write the rule again because I know at this point we should all be familiar with that. And a cool thing with indefinite integration, you probably noticed in the last problem, we don't have to write out the brackets here and put the limits here because there are none. We can just find the derivatives, antiderivatives, and do whatever with them. So the antiderivative of 5x to the 8th, our first term here, is going to be 5x to the 9th over 9. Second term, negative 12x to the 7th over 7 plus 7x to the 6th over 6 minus x, and we have to add 1 here. So 1 is 19 over 19, so to add 1, we have to do 23 plus 19, and that's going to give us 42, the meaning of life. 42 over 19, wow, what a fraction, plus 3x. Remember, we just add x to whatever constant, not multiply, we just multiply by the x there. And then what do we add whenever we have an indefinite integral? Plus c. Should have said that. If you didn't, okay, got something to practice on. So this is our integral right here. Oh, I forgot to put over 42 over 19. Let's not forget that. That's a really important step. So this is, in fact, our integral here. So we can make it look a little bit prettier, maybe simplify a couple things. So it's going to be, move this up a little bit, 5 over 9x to the 9th minus 12 over 7x to the 7th plus 7 over 6x to the 6th minus, so instead of dividing by this, we can just multiply by the reciprocal. So 19 over 42, x to the 42 over 19, plus 3x plus c. And now I'm going to go ahead and write it again just because we got some space here and I wanted to point this step out really quick because sometimes algebraic mistakes get people turned around, so we're going to write it one more time. Equal 5 over 9 x to the 9th minus 12 over 7 x to the 7th plus 7 over 6 x to the 6th minus, again, 19 over 42 x to the 42 over 19, or you could write that also as the 19th root of x to the 42 if you really wanted, but I prefer everything to be fractional. X to the 42 over 19 plus 3x plus c. And that is our final solution here. That's our solution to our integral. Okay, we made it to our last practice problem for the indefinite integration, and this is going to be a challenge problem. Yeah, we got 3 integrals instead of 1, 2, and 3 instead of 1, not just 1, not just 2. We got a whole 3 integrals, and we got a radical here, but we know how to handle those, right? Now, at first you might be looking like a V from the owl house over here. That's okay. All we got to do, I put the antiderivative rule here. All we got to do, remember to follow the order we've always been doing things. Just do things through and through and through, and we will get it done the same way we always have. So the first step I always do in something like this, I'm going to write out the integral. Again, just because we have this radical here, I don't want to be making any silly mistakes. X to the 4th minus 3x squared plus 7x minus x to the 4/7 power dx dx dx. Now let's go ahead and solve this now. We're going to do the first. We're going to integrate the first time. 5x to the 5th over 5 minus 3x third over 3 plus 7x squared over 2 minus x to the, what's 4 plus 7? 4 plus 7 is 11, so we're going to do 11 over 7 over 11 over 7. We'll see why we do that in a second. We should already know. Dx dx. So this is our first integral done. So integral 1, we're going to make a little tally over here. Integrals 1, 2, 3. So we've done our first one. So we can keep track of. So I'm going to go ahead and rewrite this just so we have the same thing. So it's just going to be x to the 5th minus x to the 3rd plus 7 halves x squared minus 7/11 x to the 11 over 7. Oh, plus c. See, even I forget sometimes. Plus c dx dx. So this is our first integral officially down. Let's do the second integral now. So the second integral we're going to start as the derivative of x to the 5th. The derivative of x to the 5th is x to the 6th over 6th. So remember, it's x to the n plus 1 over n plus 1. That's exactly what we did here. Minus x to the 4th over 4 plus 7 halves x to the 3rd, 7 halves x to the 3rd over 3 minus 7 over 11 x. And what is 11 plus 7? That's going to be 18. 18 over 7 divided by 18 over 7. Plus, this is a constant, so we just add a c. It's still a variable, so it's just going to be cx. And we have to add another c because we did integrate a second time. This is our second integral done. Now I'm going to rewrite this a little bit more conveniently. We're going to have to erase some stuff after this, I'm sure, but that's okay. 1/6 x to the 6th minus 1/4 x to the 4th. 7 halves times 1/3, so it's just 7 halves. Instead of divided by 3, we're just going to multiply by 1/3. Just simply, that's going to be 7 over 6 plus 7 over 6 x to the third minus, instead of dividing by 18 over 7, we're going to multiply by 7 over 18. 7 over 11 times 7 over 18. It's going to be, wow, 49 over 198. 198 x to the 18 over 7th power plus cx plus x dx. That's our second integral officially done. So when I did use some calculator here, especially, this is just one of those things where you can use calculator absolutely, you want to use it's going to be your best friend. So I'm going to have to erase some of this. As long as you understand how I got here, we should be good. So I'm just going to go over here to my eraser tool, top here. It's a little bit small, I'll make that a little bit bigger, don't worry. We're just going to erase some of this stuff that we already did. I'm going to try and keep the top there intact so I can have more room. Oh, looks like I should have done it in one streak. Okay, just going to get rid of some of this, if I can do it right. Get rid of some of this here. Maybe just enough space for me to complete this. Maybe make this a little bit smaller here, just so I don't get rid of too much. But we are almost done. We have one more integral to go, and then we will have fully integrated this all 3 times. Okay, now we're good. Let's go back to my pencil here. We're the right size. Perfect. So we're going to be moving upwards from here because the space is open now. So just like everything else, we're going to treat this the same. So what is the derivative, antiderivative of 1/6 x to the 6th? That's just going to be 1/6 x to the 7th over 7th minus 1/4 x to the 5th over 5 plus 7 over 6 x to the 4th over 4 minus 49 over 198 x to what's 18 plus 7. Remember, we have to add 1. 2 plus 7 is going to be 25. 25 over 7 power divided by 25 over 7. And then the antiderivative of cx is going to be cx squared over 2 plus cx plus another c. So this is then going to be our derivative this time, or our integral this time. And we can write this out to make it a little bit more easier to look at, I guess. So 1/6 divided by 7, we're going to multiply 1/6 times 1/7 instead. That's going to be 1 over 42 x to the 7th, 1 over 42 x to the 7th, minus 1/4 times 1/5, 1/4 times 1/5. And of course, these are easy to do in your head. I just want to make sure I'm doing this correctly. 1 over 20 x to the 5th plus 7/6 times 1 over 4, 7 over 24, 7 over 24 x to the 4th, minus 49 over 198 times 7 over 25. Wow, that's a big fraction, and it's going to be 343 over 4,950 x to the 25 over 7th power. Let's write that a little bit clearer. 25 over 7th power plus, so it's going to be 1/2 of this, so 1/2 cx squared, 1/2 cx squared plus cx plus c. And finally, what can we say? We've done it. This is our final integral after three integrals, 3 rounds of integration. This in our box here is our final integral. So just a couple things I want to point out. We added a plus c each time here. And we can see that this is the first c we added. It's been done to this. This is the second c we've added. It's now a constant with an x next to it. And this is the c we added in our third integral. It is just a normal plus c because it was added most recently. Now all of these degrees, what's the degree of this term? It's 4. What's the degree of this term? It's 2. Now these are the first two terms before any integration. Look at the degrees here. This is a 7, and this is 5. What's the difference between these two terms? What's 7 minus 4 and 5 minus 2? Well, it's 3. Well, how many integrals do we have here? 1, 2, 3. Remember that each time you do an integral indefinitely, each time you integrate indefinitely, you're raising the order of the polynomial, the leading polynomial, by 1. That applies to every other term as well. And even with these powers here, if I were to write it like this, well, we'd see an increase in the terms as well. Same here, of course, this is a 1. Of course, this is x to the 0, but we leave that out. There's lots of little nuances that we can do here. And this is our final integral. As convoluted as it seems a little bit, it works. And if we were to take the infinite limits here, this is what we would get. And that is all for the integral video for polynomial integration.